Hi there, everybody. In this video, we're going to talk about the motion of an object under the influence of a central force. So we're going to have some force emanating, from some central point, and it's going to be influencing the space around it, right? It's going to be, if there's an object around nearby, it's going to be influenced by that central force. So that central force is either going to be pulling the object inwards or pushing it outwards away from that central point. Okay, and this has applications to, of course, gravitational fields, but you could also imagine repulsive forces. And in this video, this is going to be a sequence of two videos. In the first video, what we're going to do is we're going to derive Kepler's second law of planetary motion, which says that when an object orbits another object, it sweeps out equal areas in equal times. Right, so the area that it sweeps out is always the same for a given time interval. So we're going to prove that in this video. In the next video, we're going to look at applying what we learn here to a gravitational field and see what we can say about what the orbits of different objects look like. Okay, so let's get at it. All right, so motion under the influence of a central force. So what we're going to do is we're going to set up a coordinate system. Okay, and we're going to imagine that the source of the force is right at the center of our coordinate system. And so that means if there's a vector, if we imagine the force vector field, the vectors that describe the direction that the force is pointing, all those force vectors are pointing directly towards the origin, right? And so we're really thinking about a force vector field here. Now, if I imagine any point in space, suppose there's an object out here. Now, that object is defined by some vector, right? That vector is r cosine theta, r sine theta. I'm using polar coordinates to represent the position of that object. That makes sense here because everything is pointing directly towards the origin. It seems to be uniform around the origin, so it seems like polar coordinates are the way to go. Okay? So the position of my object is going to be given by this. This is the position of the object under the influence of this force. Okay? Now, the force vector field is, notice that the force vector is pointing, it's parallel to the vector pointing to my object, right? But in this case, it's pointing in the opposite direction. So because it's parallel, it's a multiple of this vector. If it's pointing in the negative direction, that means it'll be a negative multiple. But we could also imagine repulsive forces that point outwards, right? So it doesn't have to be negative. But what I'm saying here is that the force vector field, which I'm going to denote capital F, is a function of r and theta. Okay? If I give you an angle and I give you a distance, we know the vector that's pointing towards the center here. All right? That's going to be the description of the force vector. Now, as we were saying, it is parallel to the vector that points to the point that we're at. Right? So it's just going to be a multiple of that vector. So actually what I've done is I've taken the r out. I've made it a unit vector. Right? So I scaled this vector pointing to that point, made it a unit vector. And it's a scalar multiple of that, right? That's one way to think about it. And so this is the scalar multiple. Notice that the function, the scalar function here, doesn't depend on theta, right? It's just a function of r. And that's representing the fact that the force vector field doesn't depend on, it's always pointing towards the center. Right? If I fix a radius, the magnitude of the force vector field is the same as long, as long as I move around with that fixed radius, no matter what theta is. So it doesn't depend on theta, the magnitude of this force. So what I'm multiplying the unit vector by to establish its magnitude is independent of theta. Okay? So that's why you don't see a theta in here. Okay, so this is how we describe our force vector field. All right. Now the object is under the influence of this force, right? So this object is going to be experiencing a force, right? And the force that this object is experiencing is the same as the mass times the acceleration of the object, right? So this has to equal the mass times acceleration of the object. So when I'm talking about acceleration, I'm talking about the second derivative of this with respect to time, thinking of r and theta as functions of time, right? So r is a function of time, and theta is a function of time. Okay, so I can take two derivatives of this thing. Okay, so that's what I'm going to be doing. So maybe what I'll do is I'll just write that like this. It's m times, I'm going to just write that same thing here. Oops, r sine theta prime prime. Okay. So how are we going to take care of all this? Well, one useful thing to do is write everything in terms of a frame of unit vectors. Okay, we're going to pick two useful unit vectors and write everything in terms of those. Okay, so one unit vector is going to be the unit vector pointing out this way. It's a vector of length 1 pointing directly at our object. All right, so that we're going to call E1. And then we're going to take a orthogonal vector pointing 90-degree angle counterclockwise, and that we're going to call the vector E2. Okay, so this is called an orthogonal frame, or an orthonormal frame, since we've normalized them to be length 1. So this is often a useful thing to do when you're trying to describe things in space. Okay, so E1, this vector, is pointing directly at the object except it has unit length. Well, to get a unit vector out of this, I just divide by its length, which is r. So if I just take the r's out, well, that's E1. How do I get E2? Well, it's 90 degrees counterclockwise. Well, it's not too hard to see. Verify this on your own. This is going to be minus sine theta cosine theta. And something might be jumping out at you right now. You might have noticed that, in fact, pause the video, think about this. How are E2 and E1 related? Is there a nice relationship between these? I'll move out of the way while you think about that. Well, you may have noticed that E2 is actually the derivative of E1, right? So if I take E1 and take the derivative with respect to theta, right, I get E2. But what we're going to do is we're actually going to take the derivative with respect to time. Okay? So I'm going to denote derivatives with respect to time with a little prime here. Well, you know that to differentiate with respect to time, you differentiate with respect to theta. The chain rule says to differentiate with respect to theta and then multiply by the derivative of theta with respect to time, right? So this is going to be d by d theta of E1 multiplied by theta prime. But as we observed, the derivative of E1 with respect to theta is actually E2. So we have this nice relationship here. Okay, and also, if I take the derivative of E2, well, that's the derivative of E2 with respect to theta multiplied by the derivative of theta with respect to time. That's the chain rule. Well, oh wait, yeah, that's right. So if I take the derivative of E2, what do I get? Well, this is a minus cosine. This becomes a minus sine. That's the negative of E1. Right? So this is negative E1 theta prime. Well, that's a cool set of relationships there. Okay? So that'll be handy for us. Now, what is this stuff in terms of E1 and E2? Like, why did we pick these? Well, we're going to write these things in terms of E1 and E2. Okay? Well, this guy right here, right? This, what's written here is R times E1, right? So what we're really doing is we're taking mass times R times, well, the second derivative of R times E1. So on this side of the equal sign, we have this. Mass times R times the cosine sign is the E1. And we're taking two derivatives. Now what about our force vector field? Well, it's equal to that, right? And our force vector field is, what's this? This is also E1. This is also E1, and it's multiplied by f of r, right? So this is equal to f of r E1. Okay, so we can rewrite all that stuff in this form. Okay, so now our goal here is to expand this stuff out. Okay, so let's do that. Well, the first thing I'm going to do is take one derivative of this and see what I get. That's just going to be the product rule, right? So I'm going to have r prime plus r times E1 prime. Okay? But we know that E1 prime, we established this relationship up here, is the same as E2 times theta prime, right? So this is the same as okay? So that's kind of cool. And what about two derivatives of this? Well, let's take another derivative. Let's use this one. So I'm going to use the product rule in each one of these. So I'm going to have this. Okay. And let's see if we can simplify this stuff. Well, we know that E1 prime is, again, theta prime times E2, right? So I'm going to replace that there. And actually, let's do all this at once. I know that this thing is given by this. I know that this thing is given by this. So let's put both of those in there. Okay, there we go. Now let's simplify everything. Let's collect all the E1 terms together and all the E2 terms together. Okay, so we've collected the E1 terms and the E2 terms. Now, why did we do that? Well, because we know that this stuff, when I multiply it by m, it's got to equal this. Or in other words, this stuff is equal to 1 over m times this stuff, right? But this stuff has only got an E1 vector, right? Now, these vectors, E1 and E2, are orthogonal, right? So it has this has an E1 component, but it doesn't have an E2 component, right? I could write this like this, right? Since these are completely orthogonal to each other, this has no contribution of E2, and this has no contribution of E1. Same, that's the case up here. So that means that this term over here in front of E1 must be equal to 1 over m times f of r. Right? I'm going to divide both sides by m. And then this term over here must equal 0. Right? So I get a system of equations. Okay, a system of equations. Right? Now, what can we do with this? Well, if we look at the second equation, if you just look at that for a while, so this is where you just kind of sit here and look at this and scratch your head and think about it, you'll see that this is actually the derivative of if what is this? Let's scratch our heads a little bit. This is this is 1 over r times the derivative of r squared theta prime. All right, do you see that? This is the same as see, if I take the derivative of r squared theta prime and use the product rule here, I will get exactly this stuff, right? If I multiply by 1 over r in the end. Okay? So what that means is that this thing must equal, I mean, the 1 over r can't equal 0, so this must equal 0. But if this part equals 0, that must mean that r squared theta prime must be a constant. And so we're going to call that constant h. Okay? So r squared theta prime, because its derivative is 0, it must be a constant. So h is the constant that it's equal to. Okay? Okay, I want to interrupt our progress there because we actually have discovered something really cool. So what we've shown so far allows us to prove an important theorem called Kepler's second law of planetary motion. All right, and let's go take a look at what this says. This is the following theorem. It says the position vector of an object moving under a central force, that's what we're dealing with, sweeps out equal areas in equal times. What does that mean? Let's go take a look at an example here. Here's an object orbiting the sun, right? Here's a planet orbiting the sun, say, or any sun, any planet orbiting, any body orbiting any other body, right? What does it mean to say that it sweeps out equal areas in equal time? Well, let's put this into motion and watch what happens, and we'll ignore this error because it doesn't seem to matter. Okay, here it goes. I can't seem to see the screen and then have it animate at the same time, so I'm going to have to not point. But you can see that what we're doing is we're looking at fixed time intervals. All right, so if we just count 1, 2, 3, 3-second time interval there. 1, 2, 3, 3-second time interval there. 1, 2, 3. Each one of these is a time interval of equal length. And what's happening here is if we look at these sectors, these black sectors that are being traced out, these 3-second intervals, all these sectors have exactly the same area. Now notice what the implications of this are. That means that when that object is far away, because the areas are necessarily bigger when it's further away because they're elongated, the object must be moving slower. And when the object is closer to the sun, it must move faster because the area that it sweeps out has a shorter diameter here, and so it has to make up for it by moving more in this direction. So it has to move faster here in order to make this area the same as these areas. But all of these areas over 3-second time intervals are all equal. And that's what Kepler's law of planetary motion says, the second law. It says that equal time intervals will correspond to sweeping out equal areas. And that really governs the speed of this object as it's orbiting the sun, right? So that's a pretty cool result. Okay, and we can prove this result from what we've seen. All right, so let's go do this. Okay, so here we go. We're going to prove Kepler's second law, and we're going to use this equation that we had, that r squared theta prime is equal to a constant. So let's think about what we're doing here. The object's moving around, and we're going to consider that at time t1 it's over here, and then it moves around, and at time t2 it ends up over here. And we're going to measure the area of that sector. Okay, well, how do you measure area? Well, you can use Calc 3 techniques, multivariable calculus. You can write that as a double integral. Area is a double integral. In polar coordinates, it's the integral of r dr d. Let me use a phi here. I'll show you why in a second. And I'm going to use an r hat here. Okay, where r hat goes from 0 to, well, it goes from 0 to out here, right? I got to span this whole region. So I got to go from 0 out to the boundary. All right, well, remember, the value of r is dependent on theta. So this goes from 0 to r of theta. And that's why I used r hat. These variables can't be the same, right, when you do an integral. This has to be a dummy variable that's different than what you called that. So that's what we're doing. This is represents the radius, but I have to give it a different name than that one. And phi is the angle, right, that goes from this value of theta to this value of theta. So I'm going to go from theta at time 1 to theta at time 2. Okay, so let's do this integral. Well, this antiderivative is easy to do. That's just 1/2. Let's pull that on the outside. 1/2 r hat squared. But then I'm going to evaluate it here. So I'm going to have r squared. Let me not write the theta in there, all right? We know it's a function of theta, so it's going to be 1/2 r squared minus 0 squared. Don't have to write that part. D phi. Okay? That's what we get when we evaluate that inner integral. Now, let's do a change of variables here. Let's call phi equal to theta of t, all right? That means that d phi is theta prime of t dt. So if I make this change of variables, put it in here, this becomes theta prime dt, all right? Now, this is with respect to t. So if, what did t go from here to here? Whenever we change our variables, we got to change the bounds on our integral to match, right, that variable. Well, it went from t1 to t2. Okay, well, here we are. Look at this. That's a constant. That's a constant. We deduced that before. Okay, well, that's fantastic. That means that if this is a constant, this is just h, right? So I'm just integrating h from t1 to t2. Well, that's just equal to 1/2 h times t2 minus t1. That's all you got to do for that integral if it's a constant, right? Well, look at this. The area is dependent on a constant multiple of the difference of the time interval, and this doesn't change. So the area only depends on the difference of times, and that's what we're proving, right? So that proves Kepler's second law of planetary motion, right? The area, and actually that's what they write here in the theorem, right, is equal to this, and it sweeps out equal areas and equal times. The area only depends on the time difference. All right, so that's it for that video. I think we'll end it there, and what we'll do in the next video is we'll continue along here, and we'll look at how to apply what we've learned here to the case where we actually have a gravitational field, and see how this describes the actual motion of planets. Because what we did here could pertain to any force field, but let's see what happens when we have a gravitational field. So I'll see you in that video.